the Zoom recording and the YouTube recording and broadcast. The Zoom recording and the YouTube recording and broadcast. Oops. Okay, Eric, do you want to go?
Yeah. Can you see my screen? It looks like
I can see your screen, yes, but maybe I'm not sure if you're in the display mode. If there's a button right here. I don't know if you see.
I don't really want to be in the display mode.
Okay, that's fine.
Yeah,
that's fine.
All right. Yeah, so I should emphasize that this talk is meant to be tremendously informal. I'm constantly tinkering with my technology for presenting, and I'm trying something new today, which is probably a mistake to try something new in real time. You know, it's hard to try something new without actually an audience to see how it works. So this is a slightly different technology from how I usually produce slides. I wanted to be able to write, have something a little bit more like a blackboard, and so I have this pad here. I find I have sensory overload when I'm trying to look at the slides and then write things, look at my notes, and there is no way I'm going to be able to see a raised hand or I can't follow the chat. So I really strongly encourage people to do whatever it is Leo wants you to do, and I encourage the chairs of the session to bring raised hands to my attention. I just won't see them. I can't think of enough things at the same time. This is the Ultracold Matter Summer School, and just start off asking ourselves why cold and why ultracold, and we got various different reasons here, and I'll work my way through some of them, and then what I really want to talk about today, and to a certain extent some of tomorrow as well, likely, is kind of I won't call it exactly historical, but a slightly detached look at the various sort of techniques and so on for making atoms very cold, making them very dense, making them degenerate, and also not so much describing these techniques, because I think the experimenters in the audience probably know about them and the theorists probably don't care. But describing whys where possible. So why is it that we've come this way? Why is the technology, why are the techniques, why do the experiments come this way? Sometimes if you understand that, the smart young people in this audience will be able to say, yeah, I see, okay, that was the reason why these experiments are going this way, but those are stupid reasons. I can think, now that I understand the reason, I realize that we've been doing it wrong all this time. And I hope that the people in the audience think that and point that out. I think that as, you know, ultracold atoms for many years were really a subject of experimentation. During my heyday, say in the world of ultracold atoms, I say that's what I've described myself doing is experimenting with ultracold atoms. Very few people say I experiment with ultracold atoms. Now they talk about working with oxygen metrology or what have you, using ultracold atoms. So these ultracold atoms become a tool. Perhaps they might even become a technology, maybe even a commercial technology, who knows? And with these things in mind, I think revisiting sort of why we do what we do is a worthwhile thing to do. So that's why I picked some topics for a very informal discussion. This is not meant to be, in no way is this going to be a review of the cool ideas in ultracold atoms these days. I had a look at the upcoming topics and speakers, and you will get for a month not just a review, but an in-depth look at most of the really cool things going on in ultracold atoms. And there's no point in my trying to anticipate all that with my talk. So presumably you're already here because you're convinced that ultracold atoms are cool. I just mentioned a couple of things that are interesting to me when I sort of think, why are we doing these things? Ultracold, for me, always the first thing was that very cold atoms, very cold temperatures magnify the effect of quantum mechanics. We think of quantum mechanics as something that, or we used to think of quantum mechanics as something that exists inside an atom, or if you're lucky, maybe inside a molecule, or if you're a condensed matter person, maybe in a superconductivity. But in the world of atomic physics, gas phase physics, quantum mechanics was inside the atom, inside the molecule sort of thing. you get to low temperatures and you can take pictures like this. This is a single, at extraordinarily low temperatures of this, a few nanokelvin, this is a single quantum mechanical wave function, macroscopically occupied by many hundreds of thousands of atoms. And it's not a trivial wave function by any means. They're doing an intricate square dance. The atoms are swirling their way around this vortex lattice. And the size of that is something like 1 millimeter across. So it's not microscopic. It's not even mesoscopic, really. You can see it with your bare eye. Well, you can see it once with your bare eye. Here at JILA, we're very worried about laser safety. So I should emphasize you could see it once with your bare eye, and then you could see it a second time with your other bare eye. But that would be it for your looking at quantum mechanics. So don't do that. The lasers are quite bright. So that's one motivation. Is like taking quantum mechanics and taking it out of the realm of the sort of nanoscopic into the essentially macroscopic, and therefore make it possible, I think. Maybe I'm stuck in the 20th century, but I still have this idea that things you can see, it's easier to understand. And so take quantum mechanics, expand it to the point where you can see it. That's going to make it easier to understand. Get to very low temperatures, especially if you're working with things like molecules or more complicated systems. The number of internal states that are occupied, the partition function of your system at room temperature can be enormous. The population and inside any one quantum state can be, a part per billion or something. You get it cold, and you win very quickly to the point where you can have prepare systems now of your initial state can be prepared for you by low temperatures, instead of having to elaborately optically pump everything. You can suppress Doppler widths, which are, if you're sort of worried about, as so many of us are in the world of atomic physics, worried about making precise measurements, various other forms of decoherence. Let's see if this works here. Not yet. Yeah, so the first order Doppler shift, delta nu over nu, is just the velocity over c. And, nu for us is, I'll just tell you that occasionally I'll put in real numbers, and I'm usually thinking about heavy alkalis, just because that's been my life, cesium and rubidium. The numbers that I put down will be progressively a little bit more wrong for sodium and still more wrong for lithium. And obviously, if you happen to be working in atomic hydrogen, it's going to be, these things will be quite a ways off. But so just sort of give you kind of an idea. If you can make yourself a little chart, T, corresponding spread in velocity. It's supposed to be a velocity corresponding spread in nu. At room temperature, maybe it's 200 meters per second as a sort of thermal spread. Works out to roughly 200 megahertz. It's one of the nice conveniences that a meter per second is about a megahertz width. You cool down to sort of Doppler temperature, Doppler cooling, laser Doppler cooling temperatures, maybe 200 microkelvin, down to only 0.15 meters per second, and you're a factor of 1,000 down in Doppler width. And the kind of temperatures that we routinely think of as ultra cold, 20 nanokelvin or something like that. This is now only
Eric, there is a question about nu. There is a question that is, what is nu physically? In the chat.
Sorry. Nu equals F equals C over lambda. It's just the laser frequency, the frequency of whatever laser you're using to study something. Sorry. Thanks for the question. Yeah, so these are Doppler widths, and then if you basically, I won't even call this a temperature, but if you confine to delta X much less than lambda, this basically, the Doppler shift basically vanishes. Of course, that's the trend these days, is to put everything into a lattice. So yeah, low temperatures, correspondingly low widths in your optical resonances. Sorry, I didn't say that. Imagine we're looking at a laser optical resonance, which is basically all that most experimenters ever do, although they may dress it up in complicated language. We can enhance or suppress or we can enhance or suppress, in any case, simplify the interaction effects. I think of a real atom as being a sort of complicated thing that looks something like that. And then I have some other real atom which looks something like that. And if they collide together, many complicated things happen, which could be interesting or not. But if we want to reduce the complexity of this, we can we can get down to the single partial wave limit. So if we have one atom passing another atom, it's got some momentum mv, and classically it's got some impact parameter b. If b mv is less than h bar, then the interactions are basically just S wave. There's just a single partial. You can describe all of the collisions just with a single parameter, possibly energy dependent parameter. So if you work out what that is, well, you want to know there's going to be some the atoms have got some range of interaction. The sort of, so we can talk about what's the maximum that the impact parameter can be. And that's something called the van der Waals length. If you've got some interaction between two particles, draw it up here. Some interaction between two particles at long range, it almost always goes as minus C6 over R to the 6th. I'd say, okay, well, what's the range of that potential? And it's a power law. So you might think, well, power law potentials don't have a range. But you can ask the other question, which is, well, suppose I start at infinity at zero energy and I roll down this potential. At some point, my momentum, at some point, which I'm going to call R van der Waals, my momentum is such that the wavelength is equal to, the momentum is equal to h bar over R van der Waals. Basically, as we roll down this potential, at some point, our wavelength becomes as short as the distance remaining to the hard collisions between the atoms. And now you actually have a real length scale, which is called R van der Waals. You solve that. You have R van der Waals, which is proportional to this quantity C6 to the 1/4 power. And it's about, it's typically about 50 Bohr radii. Anyway, it depends on the atom and so on. But from this, you can get a temperature, basically, below which you have only S-wave collisions. It depends on the species. It depends on how large this. It depends on how large this interaction term is. It depends on the mass of the atom also. But it works out to maybe 300 microkelvin. So for T below 300 microkelvin, we have S wave only. And for many people, this is more or less this is sort of a rude definition of ultra. This is where the ultra starts and ultra cold. Basically, you get to a temperature low enough that there's a single partial wave remaining. And thereafter, the interactions, I don't have to think about an atom looking like something ugly like that. My atom is just characterized by a single number, which is usually called the scattering length A. So that's another motivation for going to ultra low temperatures. And then, of course, you get to ultra low temperatures, you have degenerate gases, which of course are very near and dear to my heart. You get cold enough, and as you go to lower and lower temperatures, at some point, do you see my mouse moving on here?
Eric, there is another question in the chat that is talking about if there is only van der Waals or can be dipole-dipole or the other kind of interactions.
Yeah. Okay, so strictly speaking, if you want to have this force which goes, if you want to have a potential which has a, you could get to S wave only. There is some rule, and if I were a better physicist, I would know what that rule is. The power has to drop off as a fast enough power. I think that maybe dipole-dipole is not fast enough. So in the case of dipole-dipole interactions, it's not so easy to talk about there being a single partial wave. And in particular, because of the asymmetry, the intrinsic asymmetry of a dipole interaction, it's not going to be generically just an L equals M action. So yeah, dipole-dipole is more pathetic in this sense, but it's weak enough for most atoms that it's not usually particularly important, unless you go to a great deal of effort to make it important, as people like, say, Francesco Ferlino has by making atoms with enormously large dipoles, or the people working with cold dipolar molecules that, again, you can have really dipolar forces, interactions can become very important. I see another hand raised, Yakov.
Yes, hi. I wanted to ask about the idea of this maximal impact parameter.
Yeah.
I would think about, just two atoms could collide infinitely far away and basically not interact with that. Did you maybe mean, so what do you mean by maximal impact parameter? Is the maximum to still have interaction, or what is the exact meaning of that?
They do have interactions. I didn't make this very clear, but if two atoms have an impact parameter which is larger than that, if the impact parameter is larger than that or van der Waals, then you look at classically you look at the amount of momentum transferred, and the amount of momentum transferred is such that the wavelength, a corresponding quantum wavelength associated with that momentum transfer is large compared to that impact parameter. If you actually work out the cross sections, the rates for collisions that like that, they become very, very small. So for this, the overall cross section, the total collisional cross section, you might think classically the total, even with 1/r⁶ potential, classically the total cross section diverges, right? As you include the cross section for infinitesimally small momentum transfer. But because of, call it, diffraction effects, that rolls off. And I've swapped back and forth shamelessly between classical physics, which I understand, and quantum physics, which I don't, in order to come up with an estimate, which turns out to be pretty accurate for how that sort of classically the maximal impact parameter, which corresponds to, you take that maximal impact parameter and you square it, and that gives you a cross-sectional area, which is the basic scale for sort of like the maximal cross-section you get at low collision energy. Turns out there's resonance effects too, but this is a place to start. Does that answer your question? I'm sorry, that it was a little bit hand wavy for me.
Yeah, I was just a little confused because the impact parameter could technically be infinity and just don't collide. So you don't mean the actual maximal possibility. You mean kind of the maximum for which there still is a real interaction, kind of, right?
Perfect. Yes, that's exactly what I meant. Yeah, I'm so sorry. You said it much better than I did. Yeah, that's exactly the way I put it. That's the way I could have put it. Yeah, exactly. More questions?
Eric, I can't quite read. It says V maximum equals to, can you say what the right-hand side of that equation is?
That is R,
Escape.
That is R with the subscript V, D, W.
Oh, Van der Waals, okay.
Yeah, it's like a Van der Waals length.
Oh, okay, thank you. I thought there was something else following it. Okay, thank you.
Oh, sorry, yeah. No. Okay.
Yeah, makes sense. Thank you.
Okay, more questions? I'm happy to get the questions. There's no particular place I'm going, in the sense that I won't be disappointed if I don't finish these slides.
Yeah. So there are other questions in the chat, Eric. So you want to take a look? They said there are two, I think, dipole in free space with not polarizing field can actually come out to be an effective 1/r⁶. This happens in molecules, and then there was one even after that.
Yeah, I think the first one was a comment, just maybe.
Oh, okay.
Yeah.
Okay.
Yeah.
Okay. So
the truth of the matter is that if you look at like one rubidium atom scattering off another rubidium atom, a rubidium atom does have a dipole moment, right? Or it can have a dipole moment with a polarizing field. And so, because there's after all an S wave and a P wave, So two rubidium atoms come close to each other, they effectively polarize each other. It's R over 6. So if you want to think about it, the van der Waals interaction, the 1 over R to 6 is a dipole-dipole interaction. It's just one without a polarizing field. That was one thing I saw.
I noticed Antoine.
Okay, so yes, Antoine says that he's going to derive the van der Waals interactions in his lecture. So that's great.
Perfect. What about interactions that fall off faster than van der Waals? Yeah. I guess what I want to say is that for different functional forms, there may be different temperatures. That's where you get into this ultra cold regime. It's just that quite universally, cold atoms have this 1 over R. So their sort of long range potential looks like 1 over R to the 6. That's the thing that falls down. Or long range, that's the thing that falls down the slowest. So, which is why I mentioned that. But you can construct potentials of all other kinds. Yeah. And you'll derive all this in the next lecture. Excellent. Thank you, Antoine. Okay, so good. I think I see all this. Good. All right. Where's my? Here it is. Okay. So we talked about going on to Bose-Einstein condensation. We get down to a low enough temperature. We look at the number of occupation, the number of atoms in the ground state, and even 10 or 20% below this particular critical temperature, we find 10 or 20% below the critical temperature, we find that the fractional occupation of the lowest energy, microscopic energy state, a single particle energy state of the system becomes, order unity, even at a few 10, 20% below the critical temperature. What I would like to emphasize about this, the thing which just makes this interesting, well, there are many things that make it interesting, but I think the thing which I still find kind of astonishing so many years later is that this is not at all a brute force effect. So if the energy of the ground state is 0, and this is the energy of the first state available in a single particle energy state available in the confining potential, we can get macroscopic occupation of that ground state, even though E1 is much, much less than KTC. So this is not, even without Bose condensation, even if we had Maxwell-Boltzmann particles or something like this, if we were to cool the temperature down to a temperature which is low compared to the first excited single particle state, then all the particles will be in the ground state. And indeed, if you have an atom in a tweezer, a single particle in a tweezer, its temperature, it's to the extent that the single particle has a temperature, is low compared to that energy spacing. So that would be more, you would call that brute force cooling, I would say. This is sort of miraculous cooling due to the effects of Bose-Einstein condensation. Where does that miracle come from? Well, obviously, if we want to, we have many, many states, and we have correspondingly many, many atoms. And if we organize these atoms in here in such a way so as to minimize the free energy, then we end up getting the result is the Bose-Einstein distribution, which includes the Bose-Einstein condensate appearing at this temperature. And the key here, where does the magic happen? The magic happens there in the entropy, which of course has everything to do with the number of how we count our states. We think of if we think of there being just sort of an example, we'll call this configuration A and configuration B. And for the purpose of this discussion, we'll imagine that this whole thing is fixed. For these the distribution of atoms is fixed for all those states except for these lowest two states. And in configuration A, say I've got 10,000 atoms in the lowest state and 10,000 atoms in the next state up. And here I've got 20,000 atoms in the lowest state and 0 atoms in the next state up. If I'm in, if I have Maxwell-Boltzmann particles, then the probability, basically proportional to the number of different ways I can arrange this. The probability of now I'm in the limit of this energy difference being very small, delta E small. Then the probability of A compared to the probability of B is probability of A is equal to, I think I worked this out to 10 to the 3,000 times larger than the probability of B. In Maxwell-Boltzmann configurations, I don't care what temperature it is, as long as this energy difference, as long as this energy difference is small compared to the temperature, we'll never see configuration B. With Bose-Einstein condensation, the probability of being in configuration A is exactly the same as the probability of being being in this state. So the power of indistinguishability is it's a big effect. Sometimes you sort of think, oh well, we have this scattering, and you know, a lot of times Bose-Einstein effects, you know, we get a factor of 2 enhancement and photon anti-bunching, and it's wonderful that we get photon bunching. These bosonic enhancement effects are orders of factor of 2, but they can also be orders of factors of 10 to the 3,000, and it's what makes Bose-Einstein condensation happen. And it really is what makes there's a real sense in which a Bose-Einstein condensate is a sort of temperature. It's like being able to effectively, in a certain sense, effectively turn up the temperature of your refrigerator. Imagine you had a very strange confining potential, such that you had here's the lowest energy state, E0, and here's the second lowest energy state, E1. We know that in the case of, we have some relatively large KT, which is much larger than the spacing between E1 minus E0. Well, we'll just say E0, this is equal to 0. And so E1 is much less than KT. We know that the number of atoms in the ground state and not, it's about equal to the total number of atoms. Within, like, maybe half of the atoms are going to be in the ground state. The number of atoms in the excited state, in the first excited state, and the limit of KT being large, is KT over E1. And if we want somehow to say, I want the number of atoms in the ground state to be much larger than the number, basically I want the number of atoms in the excited state to be much less than the number of atoms in the ground state. Basically I'm saying I want KT over delta E over M naught to be much less than 1. That turns out to be true if delta E is less than KT over M naught. And that's for the Bose-Einstein condensation case. We can compare it to the the Maxwell-Boltzmann case, where to have this work, I need to have in order to have the population of the ground state be much less than the population of the excited state, I need delta E to be less than KT. So if I compare that temperature, there's a sense, and I want to say this is a very rough sense, but there's a sense in which the effect of the Bose-Einstein condensate is to divide the actual physical temperature by the number of particles of the system. So, you work very hard and you end up having a system with 30 nanokelvin, and your condensate is sensitive to it. Your condensate arranges itself in such a way to occupy a single particle state whose energy differs from the next state by something which is down by a factor. This could be 1,000,000. Could be, so you're like you work very hard to do cooling, but then Bose-Einstein condensation brings you a factor of 1,000,000. Not in all definitions of temperature, or even in most definitions of temperature, but what you're trying to do is have your condensate find the ground state for you, it's amazingly sensitive, and it's almost like having a dial on your refrigerator and say, okay, please turn up the coldness on my turn down the temperature on my refrigerator. It doesn't come easy, unfortunately. I'm here to tell you. Let's see. So fortunately, have to work kind of hard, and we have to basically play some tricks to make Bose-Einstein condensation. This is a phase diagram. This is dense. This direction. This is this is density. This is temperature. The exact location of this line in log space depends on the mass of the particle, but down here is BC and up here is not BEC. Okay, so basically it has to do with how long is the de Broglie wavelength compared to the interparticle spacing. We can also make a so on the same sort of plot, we can make a phase diagram. This is not a pressure density temperature diagram. It's a density temperature phase diagram. Up here is gas. Oops, sorry. Here's gas. Over here is solid, liquid. There's a large region which is forbidden in anytime you make a phase diagram like this. And an example is like take that.
Eric, there is a question in the chat, so I think people should be able to ask. When there is another question, please go ahead and ask yourself. Grace.
Oh, I was
go
just
ahead. Go ahead.
Asking if you said delta E has to be much less than KT or much greater in order to have condensation in the previous slide.
I'm sorry. Okay, that was fine. Yeah, sorry, I probably got that wrong. It works. It's really not much less in any case.
No.
Yeah. It works as you get this this differential. The atoms really in one state and not in the other. As long as this difference is on order of that. Excuse me. Yes, thank you for that.
Well, on order and bigger.
Yeah.
I mean, yeah. So I think the originals. Well, okay, yeah, should be.
All right, we'll make it greater, much greater, greater or much greater. Yeah.
Yes.
So I'm just discussing this forbidden region, which if you're not sort of a stat mech or sort of thermodynamic sort of person, the notion of, well, you might think, well, I can make, still learning this technology, you might think, I can make the density anything I want. I can make the temperature anything I want. Why can't I get, for instance, this X here would correspond to the exact units on the scale depends on what material we're using. So I don't have any units on the scale, but suppose I went ahead and specified my material is water and the temperature is 20 degrees Celsius, 293 degrees Kelvin. And my density is 10% of the traditional temperature of water. That would be density of water. That would be this little X right here. Say, well, I'll just take a can and I'll fill the can 10% full of water and I'll put it at room temperature and I'll shake up the can. Do I get water in the forbidden region? No, at the bottom of the can, I get a high density liquid. And at the top of the can, I get a low density gas. So all along that same temperature line, I have both states, but not this forbidden state. Okay, so why is this relevant to us? It's relevant to us because if we put the two plots together, we find out that Bose-Einstein condensation occurs always in this forbidden region. This is true for basically any material. If I go far enough out here into the not forbidden region, principal line below the BEC line, but I'm also in the solid region. And solid is the enemy of Bose-Einstein condensation, right? You've all seen scanning tunneling microscope pictures. In a solid, you can actually identify each atom by where it is in the lattice. So it's no longer, the particles are no longer indistinguishable. There's a single exception. You look at all the materials, except maybe in astrophysical conditions, but all the terrestrial materials you're ever going to find, the single exception is liquid helium. And that, for liquid helium, I would have to redraw this and have the liquid solid transition is a little bit lower. So yeah, liquid helium is not a solid, but a liquid in the BEC region. And sure enough, there is in essence a Bose-Einstein condensation at the heart of superfluid liquid helium. So that is the only exception. So in order to make a Bose-Einstein condensation, we have to be comfortable in this forbidden region down here. Which is scary, right? We're forbidden from doing it, but we should do it anyway, because are we not physicists? Are we intimidated by the notion of forbiddenness? No, we
Eric, I think there is a question.
Go ahead.
Yeah, so I was curious, what gives rise to this very particular behavior for helium?
I think it's because it has A, the lowest mass, almost the lowest mass, and B, almost the lowest interactions between any two particles. Every other atom, okay, hydrogen, molecular hydrogen, H2, has a lower mass, but it has much stronger interactions. And so it just happens to be a coincidence, or I don't know if you want to call it a coincidence, that if you go to the the region of the periodic table where you can get the very, very low masses, very low interactions, it happens to be that there's just one only element that manages still to be a liquid at that the Bose-Einstein condensation. Anything else, the interactions are a little stronger because, I should tell you that this line here moves up or down depending on the mass. If for a small mass, this line moves up. So to get to this line, this Bose-Einstein condensation line is a function of T and N, but it's basically some value of N times N over T to the 3/2. But there's some mass in here somewhere too. So maybe there's more than one mass, but there's certainly some masses and some H bars, obviously. We'll put in some times H bar and mass to the I and J as needed to get the proper things. But it's definitely the case that as we make the mass smaller, this line starts to move up and maybe can get into the liquid regime. And it does, but only for helium. There's nothing in some other universe, it might have turned out another way. It just happens to be with a particular, and in some other universe, it might have been that there are a lot of atoms, like a lot of the low end of the periodic table. Maybe neon would have worked too, and argon, who knows? Neon, I guess, is the second lightest. Neon is a little more interactive than helium and somewhat quite a bit more massive than helium. Had things turned out another way, maybe we could have had superfluid liquid neon as well as superfluid liquid helium. Or even superfluid liquid hydrogen, but no, not quite. You cool down liquid hydrogen. You can make liquid hydrogen. You cool it down, and before it becomes a superfluid, it becomes a solid.
I think Charles has a question.
Go.
Yeah, thanks. I'm just curious about what it is that defines this forbidden region.
Okay, so now we're getting into basically what happens is as you get your atoms, this is real thermodynamics. As you have we were used to thinking about gas in the ideal gas regime. As you increase the density, is that you start making the density go up and make the temperature go down. What happens is at some point they prefer to stick together, and it's a metastable thing. Leo, anytime you want to jump in here and help me out, you're the stat mech person. It's a metastable thing. You get to a point where the free energy, there's basically a little sort of a hump in the free energy. If you were to sort of plot free energy versus density, I'm not doing a very good job on this shit. Okay. Basically, just sort of imagine that it's kind of bistable. They either they get close enough together, they want to stick, in which case they stick, they go to high density, or you let them fly a little bit further apart and they say, no, the heck with this, I like to be far apart. And in between, it just turns out to be unstable. It's kind of like having Imagine you had like a whole bunch of magnets or something like that, and they're sitting on a table, and you're shaking the table. Well, the magnets are fine, but you shake the table. You don't shake the table enough. The magnets all slide together and stick together hard. And you shake the table hard enough, the magnets pop loose and rattle around. You can sort of imagine that might be sort of a bistable situation, and that's really what's going on here. Well, they're not attracted by magnetic forces; they're attracted by van der Waals forces. But they get too close together, they stick. You shake them and they break apart. And if you shake them not hard enough, which is say the temperature is not quite high enough, they stick again. And that's sort of bistable. That's when they stick, they go, whoa, they go from the same temperature, they go all the way across here to high density, and you shake them up enough, they go all the way across to low density, but they can't quite make it in between. Imagine you have a chunk of carbon dioxide. Carbon dioxide, if you put carbon dioxide, it's a solid, but there's above the solid, there's a vapor. It's sublimating. And those two states, the vapor above the carbon dioxide floating around and the solid carbon dioxide, the dry ice, those are those two stable states right there. And in between, you notice like right at the surface, there's no place where the density is anywhere in between.
It's classic, coexistence between a gas and a solid at a first order transition between the two.
Yeah.
If you try to set the density, try to set the density, you won't, it will phase separate into the two requisite states on the two sides of the first order phase transition for the microscopic reasons that Eric nicely explained.
We're used to thinking of, we almost always see phase diagrams like this, in pressure and temperature, not in density and temperature. If you look at a pressure and temperature phase diagram, there are no forbidden regions. Everything's permitted. But you take pretty much any material, and instead of plotting pressure versus temperature, you plot density versus temperature. You'll get these zones which are forbidden. It's not a special feature. It's universal for any material. They've got, and universally, it's where BEC lives, alas, because it means that we have to be in this forbidden region. What it means is it has to be, the Bose-Einstein condensates that you work with are metastable. Just as if you take a glass of hot water and you put salt into it and you heat it up and you cool it down to a point where you heat it up to all the salt dissolves. Like you put in too much salt, so you have to heat it up in order to have the salt dissolve. You found eventually the salt will start crystallizing, but it takes a while to happen because salt only crystallizes when it sticks to other salt. It doesn't stick just to water. Similarly, you look up into the sky, you can see oftentimes the vapor pressure up there will be low, and the vapor pressure of water will be high enough and the temperature is low enough that there really should be clouds up there, but the clouds need something to nucleate around, and so you can get supersaturated gases, supersaturated sky, where it's just something, a little bit happens, a little piece of dust or something comes along and then the clouds form around it. So this notion of metastability is sometimes called in physics, and in chemistry it's called supersaturation, where you can be in this forbidden region. Is very common in chemistry and physics, and it's where Bose-Einstein condensation happens. We are cheating. Bose-Einstein condensation is not a equilibrium state of matter. It's only sort of kind of an equilibrium state. It's in this metastable condition, and it only happens because the atoms aren't able to stick to each other. If I have I drew here. This is where we typically do. Here's a Bose-Einstein condensation rubidium, and we're on this log, so we're all the way down at like 10 to the -8 Kelvin or something like that, and maybe we're at, maybe this is this is 10 to the -8 Kelvin. And this is 10 to the 12. This is 10 to the 12 atoms per cc. If we were in equilibrium, we would at 10 nanokelvin, the equilibrium state. There's two equilibrium states. There's a solid, which is at the solid of just a condensed matter of any metal, and then there's the vapor pressure above it. At 10 nanokelvin, the vapor pressure of rubidium is such that in the volume of the solar system, which is like inside the orbit of Neptune, there would be less than 1 rubidium atom. That's a very low pressure gas. So this is the our metastable, what we like to think of as our nice equilibrium rubidium condensate is, depending on how you look at it, it's either 8 orders of magnitude too rarefied. Its density is 8 orders of magnitude too small, or it's, I don't know, 2,000 orders of magnitude too high, depending on how you want to figure it. So, yeah, it's worth bearing in mind that as much as we think of ourselves as doing equilibrium physics, we really aren't.
Eric, but maybe can you comment? Oh.
Go ahead, Leo.
Yeah, can you maybe comment whether this is specific to rubidium, or there's something you view as, you know, more fundamental and more general, that somehow there's something fundamental that forbids having an equilibrium gaseous state? You know, that's.
No, I don't think there's anything fundamental at all. I think this has to do with the parameters of material, given what our fine structure constant is, how much our protons weigh. In another universe, if our protons weighed something different, the fine structure constant was something different. And it's not at all universal. Helium. Helium is in okay, call it a liquid, but my understanding is that liquids are pretty much the same as gases. I think you were the one who told me that, Leo. So
Sure.
I shouldn't make such a big deal over the difference between gases and liquids anyway. So yeah, there's nothing special about it. It just happens to be our stuff.
But I meant not such a grand, distinct scale as going to a different universe. But what I mean is, other examples of alkali atoms or other condensates that have been realized that are actually not in the forbidden region?
Absolutely no, there's nothing. This is
okay.
Yeah, there's helium. There's liquid helium. That's what there is.
Okay.
Oh, but I'll make an exception for like astrophysics. Astrophysicists will tell you that there is a BCS superfluid inside some neutron star or something like that. That's, by God, that's really equilibrium. That is. But it's like neutron material or something like that, which we can't. Neutron, whatever you want to call that stuff is, quark gluon goop or something. And yeah,
at those temperatures that you need to get to, or phase space densities, things just want to be a solid. That's maybe.
Yeah. Everything does except for helium. Yeah.
Okay.
It's too bad, really. So what's going on? So how does this gas know that it's not supposed to? How does this gas here know? Can you see my mouse? Does that show up when I wiggle around?
Yes.
Yeah. So basically what happens is, if you have a condensate, if 3 atoms come close together, 2 atoms will, if 3 atoms collide, 2 atoms can stick very close together. What's a process called 3-body recombination, and release a lot of energy. And that molecule will go flying off in one direction with a lot of energy, and the atom will go flying off in another direction with a lot of energy. My statement that the Bose-Einstein condensation is a metastable state is basically saying that there's no detailed equilibrium. There's no molecules coming back the other way, colliding with atoms and breaking apart into 3 atoms. That doesn't happen. That's basically in equilibrium, those 2 processes. In fact, energy is released, and the density of molecules, the corresponding density of molecules and atoms, are so low that they never find each other and come back into atoms. And this process not only causes the condensate to disappear, these energies are much, much higher, 10 to the 10 times higher, the energies released, perhaps, than, in some cases, than the temperature of the condensate. But as they fly out, as the molecules form, as it flies out, it might crash into another atom. The energetic atom flies out and crashes into another atom, and these atoms are kicked around, and so it actually can leave behind itself a trace of heat. So it can cause both a decay of the condensate and a heating of the condensate. So how do we suppress that? Basically, the per particle, when am I going to get smart? Per atom, the 3-body rate is proportional to density squared. The two-body rate, just two atoms colliding with each other elastically, is proportional to density. This is per atom. So basically, if you have many sequential collisions, this can lead to thermalization, no problem. Three-body collisions lead to loss. So realistically, you want to have maybe you'd like gamma 2b to be, I don't know, 100 times gamma 3b. It depends on how good a thermal equilibrium you want. This is sometimes called the good to bad collision ratio. To achieve a good, efficient evaporative cooling, you'd like this number ideally to be even greater than maybe 200 or something like that. If you've already made your condensate and you just want to keep it around for a little while, maybe you could get away with this number being 10. But the fact that this ratio has to apply, the two-body rate needs to be larger, sets an upper limit on the achievable density. Again, this is species dependent, but you'll very, very rarely see a condensate. Basically, for condensates, the densities are almost always less than 10 to the 14 atoms per cubic centimeter. Maybe you can have a higher density condensate for a very short time, but not for very long. And then now if we know that the density can't be, if we know that the density has to be quite low down here at 10 to the 14 atoms per cubic centimeter, let's see, go through it. That in turn, if the density has to be 10 to the 14, let me find the right one here. This one. If the density has to be low at 10 to the 14 atoms per cubic centimeter, that tells us the temperature has to be low in order to see condensates. So basically, the temperature has to be, this is species dependent. It can depend on whether you're working with hydrogen or something, but basically the temperature needs to be less than about 500 nanokelvin. Ideally, more often you see temperatures around 50 nanokelvin. So this is why the temperatures are so very cold. You might think we need some product, but Bose-Einstein condensation happens when the density over, T to the 3/2 hits some critical value. You might think, well, why don't we ever work with larger densities and larger temperatures and still get that same critical value? And the answer is, you get up there, the condensates just don't live very long. They live milliseconds, microseconds, whatever it is. So that's what's driving us to, that's what's the ultra and ultra low temperatures if you want to do Bose-Einstein condensation. Sad but true.
I have a question.
Please.
Yes. So I'm still not clear why the three bodies collision is bad.
Yes. Let me it's a good question. Let me draw a picture for that. First, we'll ignore this because that's not what I want to talk about here. This is the space, this is the distance between two atoms. And this is the interaction energy between two atoms. Say interaction energy, like it's the rubidium interaction energy. And my apologies to all the excellent people who are working on lithium or potassium or ytterbium or dysprosium, but these things don't change very much. The atoms, the depth of the interatomic potential is about 3000 Kelvin. And there are many, many, many bound states. That lowest bound state there is just the chemical molecule rubidium-2, and it's bound by 3000 Kelvin, but there are many, many, many bound states. Imagine I have a free atom, and the free atom comes rolling along, and it encounters, so this is at R equals 0, this is the location of the other atom. So it gets very close to the other atom, it gets pulled down into the potential, it rolls all the way down, it hits the hard body repulsive wall, it rolls back again, and it goes out. So this is a classical picture, but it's a pretty good picture. So I can have an atom, one atom, collide with another rubidium atom, and it does not get trapped down there because the two rubidium atoms, when they get close to each other, they're very symmetric. You know, they have the same charge, they have the same thing, they don't radiate, you know, so they have a lot of energy, they're accelerating rapidly, but they don't radiate photons. So two atoms can bounce off each other many times and not stick. But if this atom rolls down in here, and right when it gets to here, a third atom comes and scatters off of it, this atom will take away all the energy. And this blue atom here will stick and we will remain trapped inside here. And so now we'll have this, we could call this rubidium 2 star. It's a molecule, it's in an excited vibrational energy or vibrational state, but the energy released here could be, you know, 200 Kelvin or something which is many, many, many times more energetic than the temperatures of the cloud. So these energy of both the molecule, but now we have two atoms stuck together, flies away one way, and then the atom flies away the other. They both have energies which are essentially infinitely high compared to the temperatures of the condensate of our sample. So they're gone. So that's the effect of three-body collisions. It's called three-body recombination.
Oh, okay. Thank you very much.
Sure. Okay, so
can I ask a follow-up question to that effect?
Please do.
Why does the third atom that comes and interacts with the two atoms that are colliding, why does it take away so much energy?
Oh, because ordinarily, good question. I'm going to make a new slide for it. Okay, ordinarily, these three atoms are flying around and their velocities are maybe less than 1 centimeter per second. And one atom will bounce off of another atom, and maybe they will exchange a little energy in the lab frame. And so eventually we will, establish some thermal, if I have like a number of atoms and energy, they'll share energy among each other, and I'll get some Bose-Einstein energy distribution. Anyway, so the two atoms are, these two atoms collide with each other. They come in at 1 centimeter per second, and they go out at 1 centimeter per second. But suppose we look and see what happens at the exact moment of the collision. Classically, the collision is actually very exciting. Here, this atom is traveling at 1 centimeter per second. And here's the potential. This is U, the interaction between two atoms. It's traveling at 1 centimeter per second. But by the time it's rolled down this hill here it's traveling at 300 meters per second. You might think 300 meters per second, that's terrible. That's like 500 Kelvin or something like that. This atom is crazy hot, but it's not crazy hot. It just comes in there. Classically, it comes in there, it hits the wall, it rolls up the inside wall until it comes back up to the same energy it comes in. And it turns around and rolls back again, and rolls all the way out. And off it's going now at 1 centimeter per second, except maybe it's going in a different direction, because this is sort of a 1D picture. But in fact, maybe it comes in going north-south, bounces off, and bounces off each other, goes off going east-west. But right in the middle of that collision, it's got a huge amount of energy. As long as there's no other atom around to witness it, conservation of energy says the energy comes in, turns into potential energy, goes back out into kinetic energy, everything's cool. But if it just happens to be at the exact moment of this violent collision, there happens to be a third atom which is sitting. Basically, think of it as right in between them. However you want to think about it. It's like there's a third atom here. Not that this is a two-atom picture, but I've got a third atom here, and this high energy atom, instead of coming in and bouncing off and going back, it hits this red atom. It's going 300 meters per second. Maybe this atom now goes flying away at 300 or at 150 meters per second. So it gets trapped down there. that's what gets rid of the thing that saves us, that makes two-body collisions harmless, is that they can't get rid of the energy when they're going fast. So they end up coming back out going slow. But if right down there that they can get energy by colliding with a third energy, I can conserve total momentum and total energy, and give energy to deal out energy to the atoms which are stuck together in the third atom, because this is a violent collision. Does that make sense?
Mm-hmm.
Yeah. All right. Other questions? I see there's lots of chat going on. I don't know if I should look at that. Oh, Leo's cleaning up the things I forget to say. Thank you, Leo. Okay. All this is motivation for saying that this is why Bose-Einstein condensations occur not at 10 millikelvin, not at, you might think, well, 10 millikelvin sounds pretty damn cold, right? Why isn't 10 millikelvin cold enough? The reason is that if you were at 10 millikelvin, to get the Bose-Einstein condensation, you'd have to have a much higher density than you do at 10 microkelvin or 10 nanokelvin. At 10 millikelvin, the density has to be a whole lot higher, and at that higher density, the lifetime becomes very short. I believe, back up somewhere, I'm going to take a little side. I think somewhere I wrote this, N over T. What did I write? Did I write N over T to the 3 halves? I hope I did. Let's imagine that I got that right earlier on. Okay. So how do we get things very cold? There's a bunch of standard techniques for this, which the experimenters, I'm sure, know very well, and probably the theorists have heard it at least once or twice, but I'll mention it. The first one is basically we're motivated to make things very, very cold. And one more final thing I should say is that these minimum temperatures I've discussed that you have to get to, say something less than something less than a microkelvin. These are lower temperature. You can't get to these temperatures in a helium dilution refrigerator. It turns out that if you are working with hydrogen and not a heavy alkali, the corresponding temperature is actually quite a bit higher, but they're still lower than you can conveniently get to. You can conveniently get to with a helium dilution refrigerator. So, in the 70s and 80s, there was sort of a 15-year effort to make Bose-Einstein condensation in spin polarized hydrogen just by putting it inside a box inside a helium dilution refrigerator, and those experiments did not work. And this is why, basically, just the dilution refrigerators were not quite cold enough, which is why in the late 1980s, mid 1980s onto late 1980s, when laser cooling became a big thing, everyone was working on laser cooling and atomic physics, and people were looking around saying, okay, now we can make things really cold. What would be good to do with this? A lot of people, including myself and Carl Wyman and Dave Pritchard and Wolfgang Ketterle, many other people said, if we could use lasers to make things really cold, maybe we could break this, break through this problem and get to low enough temperatures that we could work at low enough densities, that we could have a Bose-Einstein condensation, which would be stable long enough for us to look at it. So the idea behind the Doppler cooling is simple enough. You've got you have some laser, and the laser has frequency nu. I always write it as nu, but you could write it as frequency f, sure. And there's some probability of scattering. This is the probability of scattering a photon, and there's a resonance. The resonance is at 400 terahertz, and the width of that resonance is about 5 megahertz. And you arrange to have a laser coming in from the left and from the right, and you arrange for that laser to be a little bit too red. It's red so that if you have an atom here, draw ourselves an atom. And let's say that atom is moving and the velocity is moving towards the left. The atom says, oh, this is nice. If this atom is moving in this direction, the atom looks at this laser coming towards it and it says, oh, I see a Doppler shift. I think, to my mind, that laser is actually a little bluer than it would be in the lab frame. If that same laser looks at the laser which is coming from the right, it says, oh, actually, I'm moving away from that laser. I think that laser is a little redder. And therefore, the laser will preferentially, the atom will say, I like this laser, and I don't like that laser. So the photons coming from this laser will bounce off of the atoms. And every time the photon bounces up, it picks up, there's a momentum. We could say delta M atom V, call it delta M atom V is just equal to the momentum of the photon that bounces off of it. It's a little more complicated than that because the atom absorbs the photon coming in from the right, and that gives it this kick. And then it spits the photon out. And when it spits the photon out, it spontaneously re-emits the photon. It can go off into, okay, not really 4 pi steradians, but into a very wide solid angle it can go off into. And but that's a random angle. So you absorb a photon in a deterministic way and you spit it out into a random way. On average, you pick up the momentum of the photon with each scattering event. And so in the limit of the relatively low velocities, you can sort of linearize this thing and you get the, there's a force on the atom, which is equal to the momentum of a single photon times the scattering rate from the photon from the left minus the scattering rate of the photon from the right. And we can, if we're in a, we can linearize this. If we're in a region where the velocities are fairly small, that difference in scattering length is just proportional to the velocity. So we can get a force which is proportional to some constant times the velocity of the atom. So this is called lattice. The important thing is that there's a minus sign there. It's equal to minus K VA. Okay, so that's a standard trick. Been around for a long time.
Eric, where's the detuning in that formula?
The detuning is, this is the peak of the resonance. And this is where the laser is set. So the detuning here, delta, it's important that the laser is detuned red.
Right.
If the laser were detuned blue, if the laser were over here somewhere, this slope has the opposite sign. And so now you would get a, in this case, you would get a positive, you'd get a I guess it would be in effect a exponential increase in your velocity as long as they're in that linear regime.
Oh, I see. But it's in the slope of gamma L minus gamma R.
Yes.
Okay. It's that linearization. If you were not detuned, you couldn't linearize around that.
If you were not detuned, if you were flat, you'd be flat up here, and there'd be gamma L and gamma R would be yeah, it would be, I guess there'd be some second order effect, but yeah.
It's in that, it's that linearization.
Yeah, basically you want to bias the effect one way or the other. So that's what's going on. More questions about that?
Can you say something about limitation of this? I mean, at some point you slow them down enough. There's must be shot noise from
I can.
re-emission.
I can definitely. In fact, I'll say something about that right now.
Okay, wonderful.
So we've got a force on the atoms, which is equal to some some constant times the velocity of the atom. But then suppose we have an atom whose velocity is more or less zero. It's more or less zero. If I look at that same plot of the resonance curve of the atom, there's the laser, and these two, from the light side and left side, are more or less right on top of each other. Basically, gamma L is equal to gamma R at this point. The scattering from the left is equal to the scattering from the right. And every time it scatters a photon, it picks up a velocity, it picks up a momentum, p photon. And if you work it out, there's going to be a random walk. Basically, the energy is going to increase at, we'll say these two things are equal to each other, and they're equal to gamma bar, at the rate gamma bar times p gamma squared over 2m. This is the little unit of energy. Sometimes it's called the recoil energy. Just to put numbers on it, p gamma is equal to mv. For a rubidium atom, this is like the recoil velocity. The recoil velocity is about 0.5 centimeters per second. And what's sometimes called the recoil energy, which is E gamma times I'm just going to turn that momentum into a little energy. This works out to, hang on a second, about 0.5 microkelvin. So the temperature is going up because it keeps scattering these photons, and so the momentum takes a random walk. And after it's taken a random walk, if I ask what's the mean square radius of that, that's just the number of steps, and that number of steps is this many per time. So basically, this is a heating effect, basically a random walk in momentum space. This is a cooling effect, and you get an equilibrium temperature when the damping rate just balances that out. And it turns out that you can probably imagine that there's an optimal detuning. I want my laser to be just the right amount of detuning in order to sort of optimize the balance between those two. I won't derive that. In any case, it's quite difficult to derive in higher dimensions. But you find that you get something called the Doppler limit, when those two things balance each other out, which is, I don't know, it's about 300 microkelvin. Again, it depends on the particular species you're working at. Maybe 200 microkelvin, I don't know. So this is the lowest temperature you can get to with using this Doppler method of cooling. It works pretty well at three dimensions. And I don't know if that shows up. Yeah. Typically, you'll have laser beams coming in from the east, west, north, south, up and down. In principle, you could do it all with just 4 separate lasers and not 6. You just need to be able to have some lasers that span your 3-dimensional space, K vectors that span your 3-dimensional space. And this will cool the atoms down in 3 dimensions. Very powerful technique, which was, has had huge impact. It is as wonderful as it is. It's not good enough. By the way, this is equal. This works out to be equal to if you pick the optimal detuning, it's roughly equal to h bar times the spontaneous, the peak spontaneous decay rate of the basically this is the width of that resonance. Back when I was drawing the resonance, that resonance is about 5 megahertz wide. And if you work this out, so that sort of tells you that T Doppler is h bar over k Boltzmann, or we'll call it h over k Boltzmann times the width in hertz. And a convenient thing is that if those things are, you can put those things together, it turns out 1 nanokelvin is equal to about 20 hertz. So if this width is about 5 megahertz, you put that in there and you find out that the T Doppler 5 megahertz over 20 hertz per nanokelvin, it works out to 250 microkelvin. Yeah, so that's that number I had before. So this is wonderful. It's pretty good, but it's not good enough, as it turns out, because 250 microkelvin really is kind of too hot to make a Bose condensate. I'll add one more thing to it, which is there's this other sort of wonderful feature, which is if you have laser coming in from the right and the left, and the kind of molecules we work with are the ground state is an S state, and the excited state is a P state. So you have, here you can have a Zeeman shift. So if you arrange to have a magnetic field going this way or going that way, and you make your laser beams polarized, circularly polarized, then the atoms over here will experience a Zeeman shift such that the laser beam from the left is closer to on resonance. And over here is the other way around. Again, with this red detuning, you can have, if the magnetic field is going on the left side of the trap is going this way, on the right side of the trap is going this way, and the magnetic field vanishes in between, you can get preferential, if you're on this side of the trap, you can get preferential absorption based not on your velocity, but on your position, because if your magnetic field B is equal to some gradient times your displacement in the x direction, the x-hat direction. So you end up getting a force which is it's proportional to both to the position and to the velocity. So this looks like a this I was calling this K before, so we'll call that kappa. So this looks like a damped harmonic oscillator. And not that it matters, but typically under typical experimental parameters, it's overdamped. They don't oscillate back and forth. They come screeching to a halt.
Could I jump in with a question real quick?
Please.
So we were talking about the Doppler temperature, and just happens that it seems to be about the same order as where S-wave collisions dominate. Is this just a fortuitous thing, or is there maybe some lower connection there?
Well, that's an interesting question. Yeah, so the Doppler temperature happens to get you very close. I think it's probably a coincidence. For one thing, you can have atoms which have very different resonant widths. Rubidium is a very strong transition. Other atoms have a narrower transition and correspondingly much colder. I think that's kind of a coincidence. It's a terrific question. I want to think about that.
Cool.
But
Thank you.
typically, Eric, the collisions are not that big at DL or at the densities that you are working for Doppler cooling. Yes, so
Yeah,
collisions are going to be more important later.
Yes, that's true actually. But it is an interesting aspect. Can you just use Doppler cooling only? And as we'll see, there's better kinds of cooling coming up. If we just use Doppler cooling only, can we get to the ultra-cold limit? And the answer is almost, at least for rubidium, but not quite. Whereas in this next form of cooling, which I'm about to describe, you get deeply into the ultra-cold limit. Okay.
So Eric, let me just jump in for a second on administrative side. So there's we're about 9 minutes away from 10:30, so you might want to plan accordingly, particularly if we want to have some time for discussion.
I think what I'd like to plan to do is to stop here, because it's roughly halfway through the stuff that I've prepared for these two talks, and see if there's any questions. And if there aren't any questions, then we can always have a little longer lunch.
Perfect. Okay, well, yeah, that's open this up for discussion and further questions.
Could you maybe explain again why we wanted it to be red detuned as opposed to blue detuned? It seems to me like it would just change the which direction would be preferred.
Great
Like,
question. Yes, and we'll do all 4 cases actually. Okay. Let's take an atom which is moving to the left. There's the velocity, and we'll start off red. So there's our red detuning. It starts off red, but because we're moving to the left, we're moving into this one. So this guy gets shifted further onto resonance, and this one gets shifted off to resonance. So we can see that the left laser is bigger, more strong than the right laser. Let's imagine that instead, we had tuned the laser here. Now again, if I'm moving, if my laser is moving to the left, this red laser will get shifted more blue. So more blue is over here. I'm moving from the laser on the right side, so this will get shifted more red. More red is over here. So now I see that the effect of the left laser is less than the effect of the right laser. Probably I should say this is gamma L is greater than gamma R. Here, gamma L is less than gamma R. So force is to the right. Here, force is to the left. So if I'm moving in the left direction, this is my velocity, I want a force going this way. So I want this case, if I'm moving in this direction and my force is going in the same direction, then my velocity will increase. If my velocity is in this direction and my force is in this direction, this is my speed, I should say. My velocity is in this direction and my force is in this direction. My speed, I should say. I'm hearing an echo from myself. My speed will increase. And then I could take that whole thing and flip it over. But I think that this is the 2 cases that make the most sense. This is for the velocity going to the left. If I wanted to pick the velocity going to the right, pretty much everything just flips over, but I still end up wanting my detuning to be red. Should I draw that out too? I can. Yeah, let's go ahead and do that too. Here's a case of my atom moving to the right. Velocity to the right. And my laser this is my left laser. Here's my right laser. If I'm moving to the right, it's this laser which will get shifted. I'm moving towards that laser, so that laser will get shifted up. And this laser will get shifted down. So gamma right will be greater than gamma left. The force will be in the left direction. So the velocity will be this way. The force will be this way. and the dVdt will be less than 0. The speed will be decreasing. So that's the speed, is the magnitude of the velocity I want to decrease. Is that clear? Does that get at your question?
Yeah, that answers my question. Thank you.
I'd like to ask a question also on Doppler cooling. You mentioned that typically you use like a megahertz line width, and I guess you could take this lower in order to decrease the Doppler limit.
Yes.
But is it something that prevents you from using, say, a clock transition? Go to a millihertz line width and go, I guess picokelvin temperatures. Is that a possibility?
Yeah, that's a great question, actually. No, it's not a possibility. You can win by going to. It's a terrific question, and it's interesting to see why. So you start off by winning. Like if you let's see here. Rubidium is 5 megahertz. So I'm going to have, I'm going to pick my favorite molecule. Let's see, Jacobium is 1 megahertz. And yes, so this is good. My T Doppler will go down by factor of 5. So far, so good. There will be, there are some costs associated with it. As we get narrower and narrower, we know that if we scatter a photon, we absorb a photon, the photon will disappear, the atom will go into an excited state, and then the atom will decay, and there'll be a kick. This is the photon which is emitted, and that will give you a momentum P gamma. Even if our selectivity is just perfectly as good as it could be, so that it's really, really good, so that I have no difficulties. I can cool all the way down to 0 when I absorb. I'll always have to re-emit a photon, which means that there's something called the recoil limit, which is, it works out to be the T recoil limit equals, it's a few times T gamma squared over 2m. And if this recoil limit, if this is greater than our calculated T Doppler, then basically Doppler cooling doesn't work. Basically the random walk associated basically takes me out of the linear regime. My random walk can take me away from the narrow line or across to the other side, such that it's not a, how to put it, the whole picture sort of breaks down if I get down at that limit. Also, as the transition gets narrower and narrower, it gets narrower because, exactly because the spontaneous decay rate becomes small. And so then the rate of cooling, which is also important. You want to cool to a low fundamental limit, but you also want to get there before something bad happens. One bad thing that can happen is the atom can fall. Here on Earth, the atoms are undergoing an acceleration of 980 centimeters per second, which means that you think you'd like to cool down to less than a centimeter per second, you better do that fast compared to 1 millisecond, because after 1 millisecond, your gravitational velocity is already 1 centimeter per second. So because of gravity, because of the spontaneous decay, and next tomorrow, I'll talk quite a bit more about this recoil limit. Because of that, yeah, we're forced to confront that we could win only so far going to narrower lines. And so clock transitions, no. Modestly forbidden transitions with less than 1 megahertz line widths, yeah, those are possible. 500 kilohertz line widths, those are possible. And people will sometimes, I'm going to talk about a concept called the capture limit, which I'll get to tomorrow. People will sometimes do 2 stages of cooling where they first use a transition on a 5 megahertz transition, get them pretty cold, and then change their lasers to a different transition and get them colder yet. It definitely works within limits.
Perfect. Thank you.
Other questions? Well, if not, let's thank Eric for a wonderful lecture and wonderful kickstart to our school. And so we'll reconvene in half an hour promptly with the second lecture by Antoine. Thank you very much. So I'm going to shut off the Zoom and then I will reopen it just so we can have lectures separated in their recordings. And if you want to chat and relax and talk to students, feel free to use GatherTown or the Discord. Thank you very much. See you in half an hour.